Hi, everyone. Welcome back from lunch. We're going to start our next session. I would like to introduce Sarathe Jayakumar. He's principal engineer at Intel. His primary focus has been on platform architecture, BIOS, and embedded firmware, and has contributed to the industry standard specifications such as ACPI, PCIe, can you pronounce this? JDEC? It's JEDEC, and removing SMM from Intel platforms. Welcome. Thank you.
You guys can hear me okay? All right, good. Thanks, Mark. Now that we all had our lunch, let's talk about sleep states. Now we'll actually talk about SMI first. So basically, how many of you love SMI here? I love SMI too. Because it gives me a lot of powerful mechanism to do stuff inside, under the operating system, right? I can go in there, take all the cores, the full memory is available for me, all the registers that are locked are now unlocked, right? And the whole platform is my playground. I can do a lot of stuff without the OS knowing anything about it, right? So it gives us a lot of a very powerful tool for us, right? But it also leads to a lot of abuse over time. And anytime we want to do something that would require some event handling in runtime, could be system errors or some drivers invoking a DSM method, right? We drop into SMI because that's probably the most easiest thing to do, right? And it's been there for, 20 plus years since we started abusing it. And now we are at a point where the core count is increasing, right? A lot of security concerns around it. So we probably want to find a way to move things out of SMI, right? And today I'm going to talk about one of the case studies we did and demo that in a video demo, actually. So just to give a quick 2-minute overview, right? SMI is system management interrupt, and when the processor receives the interrupt, it switches to a mode called system management mode and runs a piece of memory, piece of black box code, which the OS can't see, right? And SMI is broadcast in nature, so which means that everybody gets into SMI, right? So if I initiate an SMI and we go into this mode, all the processes stall for however long it takes to finish the work and get back. Right? So there are a lot of complexity involved with multiple sockets, multiple cores, a lot of bringing them, rendezvousing them to make sure that there is no collision there between multiple processors accessing the same resource. A lot of race conditions that we're still dealing with even today. And then there are security concerns, right? SMI is highly privileged. And once you get into SMM, then you can do a lot of havoc. Right? These are all known things, right? So I don't want to dwell too much into this. So let's look at what kind of SMIs that we are going to tackle first, right? Now, when you look at how the OS interacts with the platform, we have abstraction layers. ACPI is an obvious one. And then we have runtime services, right? And OSs don't invoke SMI directly. OSs call a abstraction service, like a DSM method in ACPI or a runtime service, right? Now, underneath this runtime service is where we drop into SMI. Right? So the fact that we are dropping into SMI is transparent to the operating system. And then there are hardware events which are triggered based on system errors, some platform events, GPIOs, right, whatnot. So they also fire SMI. Again, it's transparent to the operating system. Right? So our goal is to keep the OS to the platform interface the same. And underneath the interface, how can we move things out of SMI? So we can divide this overall into 4 different categories of SMIs. We all know that we can trigger a SMI through software means by writing to port B2 in Intel platforms, right, which are basically called synchronous SMIs. And then there are SMIs that are triggered by the platform, by hardware, which are asynchronous SMIs. Right? Now, within them, we can subdivide them into those that require privileges and those that don't require privileges. Right? Now, those that, when I say privileges, I mean those that can be done only from inside SMI, like touching the flash part, SPI flash, or touching some registers which are locked for ring 0 access, but opens up for SMM access. Right? So the first category is what we're going to be focusing on mainly today, and we'll touch about the rest a little bit. So if you look at software SMI handlers that do not require privileges, meaning that I can do the exact same thing from ring 0. Right? I don't have to be in SMI to do this. There's no privilege requirement for me. But then when you look at a typical server platform, there are like 50 plus of these things hanging around. Right? And when we looked into why we have these things, it's mainly because we have a bunch of DSM interfaces that the OS invokes. Right? Like for example, for Crystal Ridge or what you call 3D Crosspoint DIMMs, if you go to pmum.io website, you can see a bunch of DSMs that are provided so that the OS or the drivers, NVM drivers, can call into the platform services. Right? So now what happens is, the question arrives, why can't we just do it in a driver? Right? Obvious question. And we should, if we can move things out of the SMI into a OS domain, right, we should do it. Right? That should be our first order of priority. But then we tried it a few times in the past, and we always got pushed back saying that, well, there's a lot of silicon knowledge, a lot of platform knowledge that the OS has to carry, which changes every generation. Right? So for example, let me give you, if you guys remember the VIA interface, now we call API in ACPI. So we had a concept of pre-shed plugin where we can have platform-specific plugins, but to maintain and distribute all those different plugins, because each OEM can have a different implementation in the hardware, right? So you have to carry a bunch of these different plugins and having proper versioning and stuff like that. So OS basically says, you know what? Give me a table called EANG table or ERST table, HEST table, right? I just use that table as an abstraction. I don't want to carry the platform information with me, right? Another thing is, if you look at a server class system, like 4-socket, 8-socket systems, we have what we call address translation that has to happen to identify the actual failing DIMM. When I get a mission check, I look at the mission check address, it gives me a system physical address, right? But I need to traverse which socket, which memory controller, which channel, which rank, bank, column, row, all the way down to the physical error in the system. So I can replace it or service it, right? Now, Linux first used to have a driver to do the translation, but it changes, this algorithm changes every generation, right? With optimizations, hardware optimizations, and new technologies coming up, this keeps moving. It's a moving target. So the Linux community came back and said, well, we can't do this. Here, give me a DSM. I'll call the DSM, and you do the stuff underneath it. Okay? And same with NVDIMM drivers, right? We have a bunch of these things we built called NFIT tables in ACPI to basically have the OS do things without BIOS getting involved. But again, we got pushback from all the OS vendors, including Microsoft and Linux communities, saying that it's too complex for us to unwind interleaving schemes to using NFIT table. So they, hey BIOS, here, give me DSM, I'll call you. You know the platform more intimately than I do, so you do deal with it, right? So we tried this driver model a lot in the past, and we come back to the same square one all the time. And as I said again, right, if there are things we have to move out of SMI into driver, first order of preference. But if we can't do it, then let's see how we can provide alternate means of doing the same thing. Right. So again, I'm talking about the first category of SMIs, which is basically those that can be done in ring 0, right? No privileges required and triggered by software. And when you look at it, most of these things are from OS calling or drivers calling a DSM interface, and ACPI is, you all know, is pretty hard to write, read, or debug, right? It's slow interpreted code, can't do much with it. And we cannot do any ISA specific or instruction set architecture specific things because it is ISA neutral, right? It's architecture neutral environment. So I can't do things like CL flash or pcommit or like sfence, any MSR operations, right, in ASL. So people drop into SMI, write to port B2 from ASL code, drop into SMI. I have everything I need. I can run native code. I'm fine. Right. Now, what if we provide alternate means to jump into a native code execution context from ACPI, from ASL code, right? If I can jump to a native code execution context, then I take away the need to drop into SMI, right? What I call the convenience SMIs, right? So basically, the proposal here is we will have a small, like I'm calling it a bridge driver, right? So we can have a ACPI driver that binds to any ACPI device object. That's a known mechanism, right? Been there forever. So I have an HID device object that I can declare, and I have a driver that binds to the device object. Right? That's standard mechanism. I also know how to call into a UEFI runtime protocol. Right? That's a standard mechanism also. I can look up the GUID and find the pointer and jump to it. So why can't we just bridge these two together? Okay. So I land in ACPI context in ASL code, and instead of writing to port B2 to trigger the SMI, I do a notify on the device object, right? A new device object that we are going to define, right? Some HID. So you notify on the device object, that's going to trigger a callback to the driver. And the driver will turn around and call the runtime service. So it's basically a sort of a jump point. And this driver is going to be a write once driver, right? Meaning that you don't have to update it every generation or things like that. It's going to be a generic driver. It's going to be pretty much a public HID, a publicly defined GUID, and the driver just connects them together. Right? So this is the basic underlying proposal that we have. Right? So this will address those SMIs that are convenience SMIs. Right? We have 50 or 60 of them today in the server class platform. So we can move all of them out. Right? And another thing with software SMIs is that software SMIs carry parameters. So when you call into a software SMI, you pass some parameters to it. Right? And if you don't do proper bounds checking on those parameters, you open up to some sort of attack surface. Right? So getting rid of these convenient software SMIs is our next order of priority. Right? Making sure that we can move this away and run it in a more less privileged code than SMI. Okay. So this basically is that I'm going to showcase or demo a error handling scenario, right? And it's called a firmware first error handling, if you guys are familiar with it. Typically what happens in a server class system is that when I get a memory correctable error, right, the system corrects it, but it also informs you. And you meaning the operating system or BMC-based manageability system. And based on the kind of errors, there's some statistical analysis we can do to find out some sort of a predictive failure of the particular DIM, right? So basically, when you fire a CMCI for a correctable error, like correctable mission check interrupt, which goes to the OS directly, OS goes and looks at the mission check banks. It gets only very limited information. What's the system address? Maybe some error code, right? So a lot of customers want much more information about the system. So we what we call a firmware first model, meaning that we get a SMI first, right? And we go into the SMI, then we collect all the errors, all the register information, a lot more information about the error, And then we build a table called HEST table, which is defined in ACPI. And then we send SCI to the operating system. The OS comes and picks it up. Right? Now imagine taking a SMI for every correctable error. Sometimes these errors happen in bursts because of some particle hits and stuff like that. So you just stall the system for however long it takes to handle those things, and very unpredictable in nature. Right? So what we are doing here is basically, instead of firing an SMI from the error subsystem, I'm going to fire an SCI, right? A system configuration interrupt, which is going to basically land me in ACPI context. Right? So once I go into ASL, now I'm going to invoke the PRM mechanism from ASL, right? Drop into the PRM handler, which is going to, when I say PRM handler is nothing but what I talked earlier, right? The runtime protocol, which I'm going to invoke from the bridge driver. So I'm calling the platform runtime mechanism, the whole thing. Now, from the ACPI context, I can invoke the PRM mechanism to build the HEST table and surface it to the operating system. Right? So if you look at what I'm showing here is I'm cutting off SMI generation, and instead I'm firing a GPIO which goes to the PCH, right? And I can program the PCH to fire an SCI, and SCI will land me in an ACPI method, and from there I'm invoking the PRM handler. It's going to build the HEST table for me. Okay? So here's the see it there? Okay. So here the memory subsystem is firing an SMI, right? And the SMI handler builds the HEST table and notifies the operating system. The OS consumes the table. That is today, right? And it puts in the event log. So I'm going to show that right now. So we are going to have a, let me see if I can stop it right here. So there is a SMI count, an MSR that you read, which will tell you how many SMIs are happening in the system. Okay. So I'm displaying it here. I'm not sure if you can see it clearly there or not. And I'm injecting memory correctable errors. Right? So in fact, when I start injecting memory correctable errors, I get an SMI, and you can see the SMI count increasing every time I get an error. Okay. And now I go look at the event log. OS shows me all the VIA errors in the event log. Right? Now let's go to the ACPI or PRM based mechanism. Same thing, but SCI, land in ASL code, call PRM handler to build the HEST table, and tell the OS about it. Now, if you look at this, same SMI count is being displayed. I'm injecting memory errors, right? And SMI count is static. It's not increasing at all, right? No SMI is happening in the system, even though multiple injections happening for memory errors. And if I go into the system event log, I see the same thing. So I achieved the exact same goal, right, of giving the OS all the information I need without going into SMI. Right? So this is one of the case studies, right, we did. And we are in the process of moving all these classes of SMI handlers out of SMI and into this mechanism. But we also need to have some sort of a bridge driver that needs to be upstreamed into the Linux kernel or inboxed into the OS stack. Right? That's where we are at this point. We have one working with Microsoft. In fact, this one we worked with, where's Peter Song here? So this one, we basically worked with Peter Song, Microsoft, to bring up this demo in a Mount Olympus platform. So we have a Windows driver doing this work, basically doing the bridging work. And then we also have a Linux driver that is also done, and we're working with the community to basically see how best we can upstream it. All right. So going back, let me see, check the time here real quick. Okay. Let me go back real quick to the other class of SMI handlers. Right. Okay. So software SMI handlers that require SMM privileges, only two things we could find. Those are the UEFI variable services and BIOS update. Right? So for BIOS update, we can go through a capsule mechanism, right? Through a reset and update the BIOS. Or in server class systems, we have a mechanism to basically do the update out of band through the BMC, right? Same thing with runtime variable updates. So even today, get variable services calls SMI. There's no need for it, right? Get variable is just reading it. I can read the flash from ring 0. I don't have to go into SMI for that. So we've actually moved that into out of SMI into ring 0. And for the third and fourth ones, these are all hardware SMIs, right? Typically for RAS events like reliability, availability, and serviceability, we call it those kind of events in the system, errors or thermal events, and people want to replace or hot plug and things like that. Those things are all hardware events, which we are migrating to the BMC, right? The BMC, all server platforms have BMCs, so pretty much all the RAS features are server specific. So we have a controller there that can do all this work for us. So this is basic outline of our strategy to see how we can reduce SMM usage. So that's all I had. Any questions?
Hello? Okay, it works. I mainly work on clients, so maybe I just haven't scrubbed through the Intel code, but we don't generally have SMIs through DISMs. But we do have like one SMI we actually care about, as far as like from the Windows operating point of view on the stuff I'm doing. And that's the one that Windows will call at the like entry and exit of Windows. I'm not sure, I guess that's a convenience SMI, but it's one that's actually called, I think, directly from Windows if you provide like the address of an SMI. And have you guys figured out how to handle that? Because we have stuff onto what Intel is doing presently.
I think you're talking about ACPI disable and ACPI enable
right,
SMIs.
that one.
Yeah. So it was there before when we had to support OSs that are not ACPI aware back in the day. So we have mechanism for an ACPI aware OS to go look at the FADT table, look at the address you talked about, and invoke the BIOS and say, hey, I'm ACPI aware. Now switch everything from SMI to SCI, right? But we don't need that anymore because pretty much all OS are ACPI aware. Been there for a while now.
It's used by our products, and it's also used, I'll have to check this round of code bases, but it's been historically been used by the Intel platform code.
Right, so we removed it actually because now all OSs are ACPI aware. We don't need a separate ACPI enable event.
Yeah, as I said, we actually have code in there.
Well, we'd like to see what
Hi. So I was curious on if I've understood the flow correctly. You have an SCI, then that ends up causing a notify, and then the notify gets called by your bridge driver, and then your bridge driver invokes the runtime service. Is that basically right? Because in about ACPI 6.1, I think, we introduced interrupt signaled events, which basically allow you to use regular interrupts instead of SCI as a way of generating an ACPI event. And so I was curious whether, if that could be built upon, you could actually cut out that first invocation of the ACPI interpreter, because if you could tie an interrupt directly to a runtime service, then the bridge driver could literally just
That's
catch
a good
the
idea,
interrupt.
actually. Yeah, let's go look at that one. I haven't looked much into that new feature in ACPI.
Well,
yeah, but
4 years old, but yeah, roughly.
I haven't looked into it.
Newish by ACPI timelines, I guess.
Right.
But yeah,
So
and
just-
OS adoption
yeah,
and
so-
so on. But
yeah,
yeah,
but-
and
but
actually, I
definitely,
think that's called the generic event model, and I think certainly Linux has generic event driver. I'm pretty sure Windows has it as well.
Okay,
But,
that's a good point, yeah.
yeah.
Thanks.
Hi, just to add to the ACPI enable event down there, I know that at HP we also look at that. I'm not sure if during a manufacturing environment when we don't have a OS loaded, whether there's any dependencies there or not. And then secondarily, one of the other categories of SMM that you haven't got covered there is the protection aspect of SMM.
The original purpose?
That's right. In that you could put secrets there for things like decrypting UEFI variables and protecting code from being tampered with that you're depending on your system.
Right. So there are certain usages where SMI is still needed, right? Mainly, as you said, for protection purposes. So, for example, even S3 script has to be saved there, right? Things like that. Yeah. And just to add to it, we do still use SMI for things that, for example, end of life events of the platform, meaning when the OS crashes, right? This blue screen. The only thing running at that point is SMI, right? When we have non-volatile DIMMs in the system, and when the power fails, you have to flush everything out before the battery, the DC rails go out of power. So we have to go to SMI and flush everything out. So there are some usages for SMI still, yeah.
So I did an audit on client platforms a while back, a whole SMM audit on almost exactly the same thing that you've done here. And one of my conclusions is that a lot of these SMI handlers are in there because there's no way to do MSR accesses through ASL. And so I was wondering, have you thought about working with the ACPI group and maybe just adding the ability to write to MSRs and read from MSRs to ASL and just do it right in the ASL and not have this driver?
For MSR handling today, yeah, you need a driver because we can't do it from ACPI directly. But we are adding some mechanisms to do that in the hardware. Because even with ACPI, what happens is, even let's say you do a driver to handle MSR, right? Mm-hmm. Now, the problem we have is on a multi-socket system, like a server class system, mm-hmm. where the MSRs are scoped based on whether it's in a socket or it's core scoped or thread scoped, right?
Well, you have CPU scopes for app processors under ACPI. Why couldn't you have MSRs under the CPU scopes in order to access the MSRs that are specific to app processors?
Right. So basically, you have to execute code from that thread.
Right.
Right. So if I have a multi-socket system, I'm running out of CPU 0, right? And I'm touching an MSR on CPU 1. I can't do that. I have to switch the context to the CPU 1's thread, right? And then write MSR from that thread. I can't do remotely.
Well, this sounds like a limitation on ASL. And on
no, it's a hardware limitation. Right? It's a hardware limitation, not.
Oh no, I understand that.
Yeah.
What I'm saying is that my inability from ASL mm-hmm. to run code on a specific CPU thread is a limit of the language, not a limit of the hardware. I mean, the hardware obviously enforces that limit because I have to talk to a specific processor. Mm-hmm. But the language prevents me from saying, sure. I want to run this piece of code on this thread. And that's a limitation of the language that should perhaps be addressed.
Correct. Yes. We need to go address that as well in the language. ACPI generally is architecture neutral, right? So that's probably the reason why it's not there. We even tried adding a gas structure, generic address structure entry for MSR, but we got a pushback from ACPI from a while back. Maybe you can, sorry?
In ARM, we have the same thing as MSR, physical system registers, and yeah.
Okay.
If there was an ASL initiative to add reading of architecture registers.
Yeah, sure. We should look at it. Yeah. Thanks. That's a good point.
Do you have any measurements of how much overhead reduction or increase is when you move from SMI to SCI?
Overhead meaning?
Latency, for example.
Yeah, so we don't have any measurements per se, but typically SMI, depending on what kind of SMI event you are handling, it might vary from 200 microseconds to 500 microseconds, right? And that's the current measurement we have on a huge server class system. But the problem with SMI is you stall everybody, right? Which means if you have 200 cores, everybody is stalled for 500 microseconds. And you can't take interrupts. So if there are any devices that require interrupts, they are lost. And you can't take NMIs, you can't take machine checks. Right? But with this one, it's the same profile as any ring 0 driver. Right? So it is single threaded and it's interruptible. Right? So latency wise, it acts like any other driver would at that point.
Okay. So if I were to understand it right, so even if the latency is a little higher, it probably is going to be better for the platform because now you can still other cores can still continue to work.
Right.
Okay, thanks.
I see on your diagram here you've listed out, well, nearly all of the solutions suggest an out-of-band option. Can you speak a bit more to what you have in mind for your out-of-band option as a way of mitigating using a SMI? Are you thinking putting this on a BMC, or are you thinking
BMC,
of
yeah.
BMC?
Right. So we have the Open BMC initiative going on, right, in the industry. So as part of it, we are pushing some deployable binaries in the Open BMC framework. So each OEM can provide their own RAS handling, for example, right, error handling modules to the Open BMC framework.
I just want to provide some information. Just the previous person mentioned the performance improvement. So last time we are in OCP, Facebook present use case, and when you have one core, you have a performance reduction is not important. Multi-core amplify, but if you are in a data center, it's if you are parallel, then one machine stops every machine, right? Yeah. So that has the biggest impact. And then Facebook in the OCP, everybody can look at it. They measured how it impact, and they fixed it with BMC method. Yeah. So it's a very useful thing for our data center performance.
So follow-up question on the use case 4, where you have the BMC to handle the out-of-band RAS. Would it be a security issue to kind of access secure registers, for example, to kind of?
In fact, I would say it's better than SMI, because what happens is SMI is in-band, right? So if you look at a data center, pretty much we have a data plane, they call it the network plane, that talks to the public IP, right? That's in-band, the host interface. And then the manageability interface, meaning the BMC talks to the manageability network, which is like an intranet, right? Within the data center, you have to be physically there or VPN into it, which means the BMC has a more secure way to get access than a public IP domain. So it's in fact better than SMI.
So you're saying BMC is the secure, trusted component, and that's why. Okay.
Anyway, I think we are 5 minutes past the hour, so I'll be during the sessions, office sessions we can talk about. Right. Thanks, everybody.